ready to go. Okay. Now, I think we covered this slide last time. So what we do is move on from this one. And the okay, going back to the last slide, you know, with what the limit of a sequence was that we had up there. If a sequence, and they quite often refer to a sequence not just listing them all, but just refer to it as set of, because remember, a sequence is a string of numbers, or whatever, usually numbers. And a sequence, since it's a set of numbers, you can refer to it as, well, if I go to write on this, it's going to be as the set, which is your brace notation, A sub n, that's the sequence that represents the nth quantity. Close it. That's the sequence, that's the set of numbers, A sub n, where A sub n follows the rule for the sequence. And in the brace, you know, the curly Q? Yeah, okay. That means a set. A sequence is a set of numbers, okay? And that set of numbers, you know, has an order to it. Everything, you know, that's what a sequence is. So the A sub n stands for that sequence of numbers that follows whatever the order is, a rule for that. If A sub n converges, like we saw in the last, then its limit, L, is unique. I mean, it can't converge to two different things or five different things. It has to be a unique number. A good way to visualize the limit is the sum of the points, and you can use anything as the first number in the ordered pair, like 1, 2, 3, 4, 5, and then plot the A sub 1, A sub 2, A sub 3 as those things, and you'll get something that looks like this. Here are your, if this is your sequence, whatever that value is, A sub 1, there's A sub 2, there's A sub 3, A sub 4, A sub 5, A sub 6, A sub 7. Plot them against the 1, 2, 3, 4, 5, 6, 7. Just to get them to stringing out there. Okay. If that's your sequence, and you know that this sequence has some limit, L, and here's L, okay? Now, there's your sequence, and it sure looks like, and this over's here. Where I put this. By the way, I was going to make another announcement to the class, but all three of you students have paid, so you don't really care that they were canceling all non-paid students, so I wouldn't go into that. Well, I guess I should. If you have any friends that maybe have not completed payment, please let them know they need to do so or get in touch with Student Financial Services or the business office as soon as possible. Okay. So here we have a sequence of numbers, that's the pink dots here, okay? And we know this has a limit L. So that means somewhere out there in the sequence, for any epsilon, now they happen to choose this epsilon, okay? They could have chosen an epsilon like that, or that, you know. This one, you could have started right here, but this one, but you could choose even smaller, like this. At some point, after some value n, all the A sub n's are going to be within the value epsilon of L. L plus epsilon or L minus epsilon. Very similar to what we did for derivatives, what we did for actually integrals too. We didn't use epsilon necessarily, but that's what you're doing. For any epsilon, the dots eventually remain within the epsilon band around L. As big as you want to make it, or as small as you want to make it. I mean, you could do it just real tiny. You just have to go a few more places, and then somewhere out there, all those, if this is the limit, somewhere out there, they're all going to be within whatever epsilon you choose. Okay? And that's what it means for this to have a limit, L, for any epsilon you happen to choose. Now, Okay. This happens to be the graph for example 3. So let's do example 3 and then we'll look at the graph. Here's your a sub n. Let me get my pen activated. I can't get black because it'll turn off the screencast-o-matic, so I'll do a dark purple. Okay. Let this be your a sub n, and that's going to be n plus 4 over n plus 1. Now, I don't know if you, just looking at that, can tell whether that converges or not. It's really not hard to tell that it does converge, but one way you can do it is to start plugging some numbers. We can start n equal 0 if we wanted to, and then a sub 0 would be 4, right? A sub 1 would be a sub 1, that would be 1 plus 4 over 1 plus 1, 5 over 2, 4, 5 over 2, or 2.5. What's the next one? A sub 2. 6 over 2, and that would be 6 over 3 would be 2. So it was 4, 2.5, 2, yeah, that works. Next one. Seven over 4. And 3 would be 7 over 4. Now, I'm not sure they got their graph right, but generally it's right. I don't believe we already did for 1. 1 would be 2.5. That's not right there. But after a while, it does close. Okay? So you could do that and say, yeah, they're getting closer and closer and closer to some value. Okay? That's one way you could do it. There's really an easier, it's a little more abstract, but I think it's ultimately easier to do. Do whatever trick works, okay? And here's what I would suggest. Rewrite that as n over n plus 1 plus 4 over n plus 1. Would you agree that that's the same thing? Okay, right. All right. Now, to me, this is easier to see. That has a limit, okay? Let's just, I mean, you can start with 0, do 0 over 1, 0, 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6, 6 over 7. What's that heading toward? Pick a big end. 10 over 11, a bigger one. 1,000 over 1,001. Say again? It's not diverging. It's actually getting closer and closer to 1,000 divided by 1,001. Do that on your calculator. See what you get. Getting close to 1, exactly. Okay, now, let n goes to infinity here. 4 over a huge number is getting close to 0. Right? 4 over 1,001 is very close to 0. So this is going to 1, that's going to 0, so this is going to 1. Okay? Now it may not be quite as easy to see with that, especially if you plug in numbers, that's getting close to 1, but it is. Now here's actually an even better way. And by the way, perfect attendance, way to go team, keep it up. Okay. All right. Here's actually the more elegant way to do it. Whenever you get n going to infinity and you have n in the expression, do this. This is legal. Divide numerator and denominator by n, or if you want to call it, multiply 1 over n by the numerator and the denominator. This would be n over n plus 4 over n over n plus 1 over n. Now that's legal, isn't it? As n is going to infinity, the 1 over n is a number, right? All right. So you're multiplying the same number by the numerator and the denominator. That should be the same equivalent form, right? What is this? 1, and as n goes to infinity, that's going to 0. And this is 1, that is 1, n goes to infinity, that's going to 0. So this is 1 over 1, which is 1. To me, this is probably the best way to do it, okay? Rather than start plugging. But they did, even though they graphed it wrong, it's getting closer and closer and closer to 1. Numerator is always a little greater than the denominator, but when you get far enough out there, like n equals 16, that would be 20 over 17. It's just a little bit more than 1. And 1,004 over 1,001, just a little bit more than 1, okay? Getting closer to 1. But this is sort of the classic way of dealing when you just have n's there. Divide by, because n's going big. It's never going to be 0. Or don't let it be 0. You can start the n at 1 or somewhere. And then this is a legal move. Okay? Notice they didn't let n equal 0. They started with n equal 1. But again, their values are right. But it is going. And they got close to 1. Okay? Make sense? Now, they say prove formally that the limit as n approaches infinity of a sub n is equal to 1. Now, actually, to me, that's a good enough proof. Okay? It's perfectly legal. But I think what they want you to do is use the definition. Okay? For any epsilon greater than 0, there is a, and you go through all that. And I think they actually start the process here. No, they don't. Okay? Thought they did. The definition requires us to show for any epsilon greater than 0, that's how you start a lot of proofs, there is a number n, and what you have to do is find the number, m, such that for all and since the limit is 1, for all that the difference between your sequence a sub n minus 1 and the limit, the absolute value of that is less than epsilon. That's what you're trying to prove. Somewhere out there, epsilon's going to, the value's going to be in between plus and minus epsilon. So that's what that's saying. Okay? So that's what we're wanting to prove, that there is some epsilon out there, and this is true for all n greater than m. Okay? It may not be for the first ones, but after some distance, it will be for the later. For all past that, that will be true. Okay? So basically what you have to show, what is your a sub n? A sub n is this thing. So this will be the absolute value, n plus 4 over n plus 1 minus 1 less than epsilon for all n greater than some value m. Okay? Now, what you need to do is put this over the same denominator, right? In order for you to do that subtraction. So that's going to be n plus 1 over n plus 1. That's 1, right? Okay? So if you do subtract your numerator, you get n minus n, those go away. 4 minus 1, that would be 3 over n minus plus 1. needs to be less than epsilon. Okay? Right? Now, what we need to do is find a value in m that n's greater than. Okay? So how are we going to get there? And by the way, we can drop the absolute values now because we don't have any more subtractions in here. So this thing is 3 is greater than 0. N plus 1, we can choose the n's large enough that it's greater than 1. So that's going to be positive. So this thing less than epsilon. Okay? So what can we do at this point? Well, since n plus 1 is greater than 1, that's our assumption, right? We can multiply both sides by n plus 1. So that would give us 3 is less than epsilon times n plus 1. But we want epsilon greater, and sure enough that's going to give it to us. So let's multiply that out. That would be, let's flip sides, and that would be epsilon n plus epsilon is greater than 3. I just flip sides there, right? See what I did? Okay. Now, we want to isolate the n because we want to come up with some value m. Okay, you got the n here, you got greater than here, so let's subtract epsilon from both sides. And that gives you epsilon n, that goes away, is greater than 3 minus epsilon, right? Well, divide both sides by epsilon. Okay, what do we have then? This goes away. That means for all n greater than, I'm going to write it this way, 3 over epsilon minus 1, right? 3 over epsilon minus epsilon over epsilon, which is 3 over epsilon minus 1. So you give me an epsilon, however small you want that to be. Pick an epsilon, as small as you want it to be, but it has to be greater than 0, of course. Give me an epsilon. 1/2, so 0.5, okay? So if you give me an epsilon 0.5, I need to find an m, and anything past that m is going to guarantee that his has a limit of 1, okay? Anything past that m. You gave me 0.5. Actually, I like the 1/2. Let's go back to 1/2. So this will be 3 divided by 1/2 is the same as 3 times 2, right? 6 minus 1 is 5. For any n greater than 5, guarantee this is going to be less than that epsilon. You gave me an epsilon of 0.5. I'm sorry, you just did that. 0.1. Then this would be 3 over 1/10. That would be 30 minus 1. Any n greater than 29 would guarantee you're within the epsilon. If you say, like they do in statistics sometimes, I want a p-value of 0.001, okay? So I want to guarantee that this epsilon is still a positive number, that you're within that unit, okay? So that would be 1,000, okay? 3 divided by 1,000 would be 3,000, right? 3 times 1,000. 3 divided by 1 over 1,000 is 3 times 1,000. 3,000 minus 1, 2,999. Any n greater than that, you guarantee you're going to be within epsilon. So you see, you've done it. You've shown that this indeed has a limit. So that's the formal way to do it. What you're trying to do is, for any epsilon you give, come up with an m, such that the difference between your value, your nth element here, and 1. So that difference is going to be less than epsilon. Plug and chug. Okay. Get it to work. All right. Now, Okay. I was trying to see where in the world this is. Here's figure 4. There's no problem with this figure 4. Oh yeah, I think I may have mentioned it to you before. Okay. This is a function, cosine n. A sub n is equal to cosine n. Does that have a limit? N, assume, is measured in radians. So when n is equal to 1, if you n is equal to 0, cosine of 0 would have been 1. Obviously, we're not counting that. N is equal to 1. If you do 1 radian, you're something near just a little bit less than 0.5. Okay? Cosine of pi thirds would be 0.5. So cosine of 1 radian, which is a little bit less than pi thirds, would be a little bit less than 1/2. Okay, maybe a little bit greater, somewhere in that neighborhood. Cosine of 2, that's somewhere in the second quadrant. That's going to be negative. Cosine of 3, that's awfully close to cosine of pi. Cosine of pi is negative, so negative 1. So this is awfully close to negative 1, like 0.9 something or another. And then you keep on going, and you see you always have values between -1 and 1. You can't get outside there because cosine can never be outside that. So it's not going to infinity anywhere, but neither is it converging anywhere because it keeps going somewhere between plus and -1. I mean, if you did, you could connect the dots almost, and you have the cosine curve. And you're just picking, not quite random, but you're picking dots off of that curve, and they could be anywhere positive or negative between plus and -1, but never converging to anything. So there is no epsilon that you can guarantee 1, but for any epsilon greater than 0, like 0.1 or even 0.5 or 0.9, you can never guarantee that all from some point on they're always going to be beyond that. They never converge. They keep the scatter up always between -1 and 1. Okay. Now, this, yeah, okay, I knew it was coming up somewhere. This was that first step that we took in our proof of the other one. Since the graph showed up first, I thought the proof was going to do it, and it didn't. That was the first step we took, that the sequence minus the limit, that difference is going to be less than epsilon for some n greater than m. What you are going to do is using this to arrive at n. Okay? So that's what the process was. All right. Now, just like the cosine n function, you saw never converge to anything. Similarly, you could do, if you have a function that does converge to something, then some somewhat random, but not really random, representation of that will be converging to the same thing. So here is a function, f of x, the line here, and it seems to be converging to L. That means that the sequence that you get from that function is also going to converge to L, and vice versa. I should blow this up, sorry. Okay. All right, a new addition to the class? Yeah. Okay. Let me get your name, please. A little louder. Okay. Last name? Muniz. Oh, yeah. I've had you before, right? Or summer. Yeah. Yeah, okay. Okay. M-U-N-I-Z or easy? M-U-N-E-Z. Easy, okay. And what's the first name again? Faith. Faith, hey, I remember now. My hearing's bad. And you go by Faith, right? Yeah. All right, we've just increased the class size by 25%. Okay, good. By 33%. Good deal. A little more. Okay. So we're up to 4 now. Okay. Someone else was asking, he said, are you teaching all those little classes? I said, well, they all got at least 3 in them. And this morning class did have 5, but it dropped back to 4, right? Okay. And then the second class this morning, I think was only 3, or maybe it was 4. Oh, there it is. Yeah, it was 4. Now this one's 4. And my afternoon class, last time I looked, has 3. The late afternoon class. And one of those hadn't paid, so it may only be 2. So I got 4, 4, 4, and 2 or 3. Okay. All right. I guess all those added together would count for one class as far as students go. But I'm not worried about that. I'm married money. Okay. So basically what you're getting at here is if f of x, if you have some function f of x, that's the pink line here, the continuous function, if that converges to some limit L, then the sequence a sub n, where is equal to f sub n, that you can come up with some function of the thing here, just like we did before. Remember we said we just choose 1, 2, 3, 4 being our first digit, the first order coordinate in the ordered pair, and then let the f sub n be the y value, you know, the value here, then that also is going to converge. We saw that the cosine function doesn't converge, so therefore its sequence doesn't converge. But if a function does converge, then its sequence that you just plug in the ends, it would converge. So that's represented by the dots. Okay? Now, if by chance you choose an epsilon down here, certainly these values are out, but just get some n past that, and it looks like maybe n equals 3. Any n 3 or greater, that would work. Narrow it down even more, you might have to go way down here somewhere, and any n 12 or more. That's always going to be the thing. So yeah, that's how we do. That's what we're basing it on. Okay. Now they did give, I think, okay, they did give an example here. I think we ought to do. I don't know if this is the one that they plotted. I don't think so. But let's see. If this is your sequence, a sub n equal n minus 1 over n. Okay, certainly n shouldn't start with 0. That's going to be undefined. Okay? But I've already told you a hint on what to do. What was that? Multiply numerator and denominator by 1 over n. Remember, n is something greater than 1, greater than some positive number there, and that's always a real number. So if you do that, that produces in your numerator n over n minus 1 over n, and in the denominator n over n. What does that converge to? N over n is 1 minus 1 over n over 1. As n goes large, 1 over n is going to 0, and that's 1 over 1. So that converges to 1. So we know that converges to 1. Okay? But the other way you could do is say, give the function that does that same thing, f of x equal x minus 1 over x. Does that converge? As x, say again? Yes, it does, and it converges to 1. That would be 1 minus 1 over x, okay? And as x gets large, that, of course, is going to 1, okay? Now, that's not necessarily this one, but if L happened to be 1, That's probably not too far off. I don't think it plots to be exactly like that, but it would be something like that. Okay. So let's go to Theorem 1. We've had definitions. Let's go to the theorem. Oh, and by the way, Faith, I should have said this when you came in. I don't have the course set up now. You took my course in the summer. Was I using Integrity then? I think I was.
Yeah.
Okay. They've done away with Integrity. Our school didn't want to pay for it, so they got a cheaper, and it is, thing, and it's called Screencast-O-Matic. So I'm using that. But it's more work on my part. What you get is about equivalent. It's not quite as nice, but it's about equivalent. And here's where it loses though. I'm recording in it now. That's what this is doing. This is 31 minutes and 18 seconds in counting that I'm recording. What I have to do is at the end of class, end the recording, tell it I'm through, and then send it to YouTube. Okay? So it doesn't go straight to Blackboard. I have to send it to YouTube. Now, Integrity, we go an hour and 15-minute class would probably load to Blackboard in 15 or 20 minutes, something like that, okay? This one, an hour and 15-minute class is going to take 45 minutes at least to load to YouTube. It's just a lot slower. But you still can't see it unless you know where my account is. So what I have to do is set up a playlist in YouTube to put it in and then link you to the playlist. I haven't done that yet. Okay. In fact, I haven't done much in this class yet. I've got the syllabus, but I've got to make a few corrections. I've got the research paper instructions. I've made those corrections, but I don't have them on Blackboard yet. I've got my locator card done, but I don't have that on Blackboard yet. This doesn't, what I will do is load all the PowerPoints. As lousy as they are, I'll load those to Blackboard. That's not been done yet. And then I'll also load any of the sites that either students have given me or I found myself that look like they might be helpful to you, websites, other YouTube videos, other things. I'll put those out there. I think I've got a few of those. And then, finally, I'll put the YouTube video link out there. It'll say Math 227 YouTube videos. That's what it'll say. You click on that, you'll be able to hear the first class where we went over the syllabus, went over the research paper, went over my locator card a little bit. We went over safety, we went over that kind of stuff, okay? And we started section 2.1. And that's where we're continuing today. So any of today's lecture you'll be able to pick up after it loads to YouTube, after I put it in the playlist, and after I put the thing. Hopefully, I'm going to stay late today and get as much of this done as possible. I can't guarantee I'll get it done today, but I'll try. Tomorrow I have very few office hours, but I'll try to I've got about 30 minutes after my first two classes, but then in the afternoon I'm here. So I probably won't get much done tomorrow, but Friday, anything I haven't done so far, I'll try to get done then, by then. And then next week, Monday will be if I don't have it done by the beginning of Monday, hopefully by the end of the day on Monday, I'll have it done. I'll work on it some in the weekend too. But the trouble is I usually don't like to take on the DVDs or CDs because I don't want them to get broken in my backpack or something. So anyway, I'll try to get those caught up so you can pick up anything you missed. All right, here's Theorem 1. A sequence defined by a function, what we were just talking about. If the limit as x goes to infinity of some function f of x exists. In other words, if that function is heading towards some limit as x goes very large, then the sequence a sub n equal f of n, that's just picking out points on that same function, it converges to the same limit. It's got to, okay? So the limit as n approaches infinity of a sub n is going to be the same as the limit as x goes to infinity of f of x. This is a continuous function. This is a sequence. Just a set of numbers. That set of numbers will, if the a sub n is defined this way, converts to the same thing the function does. And conversely, if f of x doesn't converge, neither will a sub n equal f of n. Okay. Now, I think we're ready to do example 4. Let me see if they have. I don't think there's a slide for it. No, there's not. Okay, so let's just do it here. Here's example 4. Find the limit of this sequence. Okay, 2 squared minus 2 over 2 squared. 3 squared minus 2 over 3 squared. 4 squared minus 2 over 4 squared. 5 squared minus 2 over 5 squared, ... There's your sequence. Not very pretty form, but there's your sequence. Okay. It says find the limit of that sequence. Now, frankly, what would be the first thing you would be tempted to do? Rather than having to write all those numbers down, remember what we called the a sub n before? It's the general term. So I would write the general term of that sequence. What do you think it would be? N squared minus 2 over n squared. And this is good for n greater than or equal to 2, or greater than 1, however you want to say that. Not good for n equals 0, don't even try it. N equal 1, don't mess with that one either. They started with n equal 2. Okay? Now, I've already shown you what I think is probably the easiest way to determine this. And what was that process? 1 over n squared. Pick the maximum exponent for your n over 1 over n squared. And what does that give you? N squared over n squared minus 2 over n squared over 1. Yeah. Okay, so this is 1 and that's 1. And guess what? As n is going to infinity, 2 over n squared is certainly going to 0 pretty quickly. So that's going to be 1. Okay? To me, that's the easiest way to do it. Okay? You could go to the function, which I think is what they want you to do. And by the way, in your text, they wrote the general term incorrectly. Okay? They said it's 1 minus 2 over n. It should be 2 over n squared. Did your book get it wrong? Those who have books. Now, you have the older edition, don't you? Is this one? It's wrong. Is the new paper, is that wrong too? Yeah, that should be an n squared. Okay? You can change it. Okay, that's fine. You can do that. And then the next line is wrong too. Every place they have it. Well, in fact, f of x is equal 1 minus 2 over x squared. Okay? They missed it there. They missed it in the next. They missed it in the next one. The answer is the same. Okay? But you, okay. And then they carry on through. But shoot, looking at this, you can see the answer. Why mess with the function? They said to, so you could do it. F of x is equal to, and I would use this form, 1 like they did, 1 minus 2 over x squared. Okay, except they left off the square. Okay, well then what's the limit? So it seems like they go round and around their ear to get, or elbow to get to the ear, and it doesn't get any better. The limit is 1. Okay, and they do it by taking the limit of the function as well, as x is going to infinity. Okay, and it comes out being 1. So I see no advantage in that case to do it. There may be other cases it will be, but in that case, you can see that's the limit there. Why mess with the function? But you can. It works. Now, they don't have example 5 here either in the text. I mean, it's in the text, but they don't have a slide for it on the slide set. So I'm going to erase all the ink and let's do example 5. Calculate this one. The limit as n approaches infinity of n plus log n over n squared. Okay? I didn't give you a bunch of numbers there. They give you the general term. Okay. Now, this is one of those cases where it is advantageous to change to the function. So what is the function? What variable you want to use? Everybody's favorite or something else? X. Okay, I figured everybody. Okay, x goes to infinity of, and what would be the function then? Everywhere you see an n, just change it to an x. X plus log x over x squared. I just can't. I said do it and then I didn't. So let me clean that up a little bit. Cleaned it up too much. Okay, so there's the functional form. Now, if in another life I'd ask you what the limit of that is, what would you do? Throw up your hands? I hope not. All right. Hopefully you'll remember. Well, let's just plug in and see what we get. If you plug in infinity, that'd be infinity plus log of infinity. Both of those are going to infinity over infinity squared. Well, that would be infinity. So this is infinity over infinity form you can't tell anything about. But there is a rule that you can use for 0 over 0 or infinity over infinity. And there's a couple of others you can use it on. Good old French name. L'Hopital's rule? Is that what you were saying? No, you didn't. Well, that's what you should have said. Say yes. Okay, that's what I was saying. Okay. That's what we use. L'Hopital's rule. Does anyone remember what you do with L'Hopital's rule? No, you take the derivative of both the numerator and denominator and then do the limit again. L'Hopital, and if you read up on him, you'll find out he probably didn't invent that. I think he studied under one of the Bernoullis, didn't he? And the Bernoulli had used it, but he wrote it up and got credit for it and didn't do it. And he got that Bernoulli pretty mad at him too, because the Bernoullis were pretty short-fused people in general. So I didn't mean them too badly, but it was sort of a controversy. But he got away with it, and everybody calls it L'Hopital's rule, even though he probably didn't come up. So let's take the derivative of the numerator. What's the derivative of the numerator? Say again? Okay. Derivative of x would be 1 plus 1 over x. Okay. Over 2x. Exactly. Now let's let x go to infinity. Well, this will give you 1 plus 0 over infinity. So that'd be 1 over infinity. 1 over infinity would be going to what? 1 over to an extraordinary high number would be 0. 1 over 10 million. That's awfully close to 0, right? Okay? So this limit would be 0. Okay? And because that limit is 0, the limit of the first function was 0 by L'Hopital's rule, and because of your sequence defined by a function, that sequence would also be 0. Okay. Now, that's the formal way to do it. Here's sort of, and I hope this doesn't confuse you or get you any problem, but I look at it this way. When n is going to infinity, everything's blowing up, right? But n doesn't blow up as fast as n squared, right? Huge number over huge number squared, huge number squared wins, right? It gets bigger faster. Well, log n is going big, but it's not going nearly as big as even this one does. So basically, these are poking along, and that one's getting big really, really fast, so this one wins. It gets big so much faster, so therefore it's 1 over a big number, or something over a big number, and the big number wins. It's going to 0. Okay? So you can almost look at that and guess it, but this way gives it to you exactly. Like I said, I have some weird ways of looking. Yes? Example 4. Okay, let's see if I can go back to it. This one here? No, that wasn't. It wasn't. No, I erased it. Yeah, okay. Let's go back to example 4. Okay. Are you okay with the general term? Are you okay with this? A sub n is equal to n squared minus 2 over n squared. Are you okay with that? Okay, that one's all right. Okay. Now, what I did, and there's a couple ways to do it. In fact, what they did, okay. What I did was divide everything in numerator by denominator by n squared. Okay? What they did, they split up this one. Either way is fine. They split this up to be n squared over n squared minus 2 over n squared. Okay? This is 1, right? N squared over n squared, no matter what n is. 4 million, that's still 1, okay? And then this is going to be 2 over an enormously big number. 2 over 4 million is awfully close to 0. So that's going to be 1 minus 0. Okay? Yeah. What I did was the other way, I think because the manual suggested it to me, but it doesn't matter. N squared over n squared minus 2 over n squared over n squared over n squared. I divided both everything in the numerator and the denominator by n squared. So it gave me 1, 0, 1. And that's still 1 over 1 is 1. Okay. Does that answer what you're asking? Okay, good. All right. So that was example 4. That was example 5. I think we're now ready for example 6, right? You might say, I can almost hear you mumbling in the background. Why do we ever need this for? I mean, this is just making up stuff, you know. Didn't I hear you mumbling that? I thought so. Okay. All right. Here is something real. This came out of basically quantum mechanics. Actually, before quantum mechanics, maybe. A guy named Balmer had just noted that he could calculate the wavelengths that were coming out of a hydrogen. When you excited the electron, the only one electron in hydrogen, when you excited it and it fell back to its original level, you got certain wavelengths of energy. They were discrete, a spectrum. Okay? Actually, the first few were discrete. After a while, they sort of melded together. And these are the Balmer wavelengths, and they fit perfectly hydrogen. When n is equal to 3, sort of bums me out that they, let's see, they never give it in the slideshow. Sorry about that. Irritating. Okay. Here's what the Balmer wavelengths are. Calculate the limit of the Balmer wavelengths where B sub n, I wonder where the B came from. okay, never mind, Balmer, okay, is equal to, nice round number, 364.5 n squared over n squared minus 4. Okay? It said calculate the limit of the Balmer wavelengths, and here's what they are. And these are, by the way, in nanometers. Okay? Where n is greater than or equal to 3. Don't start anything below 3. Okay. Why? What's the first number below 3? Integer. 2. What happens if you put a 2 in there? You get a 0 in the denominator. You can't do it. So don't do it. Okay? Don't try out n equals 0. That will give you a negative. I've never seen a negative wavelength. Have you? Okay. Don't use 1. That would give you a negative wavelength. Don't use 2. That would give you undefined. It blow up. Goes to infinity. Start with 3. From 3 on, it works fine. Okay? And if you want to try it, try it. 364.5 times 9 divided by 5. Try it. Punch it in on your calculator. See what you get. Quantum mechanics, Niels Bohr, I believe it was, came up with a model of the hydrogen atom, and it fit the Balmer series perfectly. 364.5 times 9 divided by 5. What do you get? That? 656. Second? 656.1, blah, 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 blah. Right. Okay. Just 0.1, exactly. Okay. Actually, yeah, that's right, because you're dividing by 5. It would come out exactly. And then you could do 4. So that would be 364.5 times 16 divided by 12. It probably won't come out exact, but it might. I don't know. 486. Does it have a decimal or not? No, it comes out exact. Fantastic. Okay, let's do 5. 364.5 times 25 divided by 21. Seems like to me this would almost have to come up with a decimal, but we'll see. Get something close to this with more decimals. Yeah. Okay. So 433.9. Keep on trucking, and they went by 1s up to 7, then they jumped up to 10, then they went to 20, then to 40, then to 60, 80, and 100, and it looks like it's going to be around 364.6 or so. I think you'd have to do a bit more. I would do 1,000 just to see if you're still at 360. Let's do 1,000, see what we get. 364.5 times 1,000 squared would be 1,000,000 divided by 999,996. Okay. See what you get. $531. 501. 364.501. Okay, so it got down to 0.5. You can keep going and see if it keeps getting smaller. Actually, it probably does. Okay, but is there a limit? Okay, it would seem so. Okay, it would seem so. But most of the time, we're really not interested in what the limit is. This is a math course, so they are. But in the reality, we're interested more in those discrete wavelengths up here. Because frankly, you get on a thing and you're trying to distinguish between these wavelengths. And these are nanometers, remember? Those are 10 to the -9 meters. Okay? just to give you an idea of what a nanometer is. I think I have in my pocket a dime, okay? That dime is about 1 millimeter. So let's slice that dime, imagine it, into 1,000 equal slices, okay? Then you've got 1 micrometer. Then take one of those tiny little slices and slice that into 1,000 equal slices, okay? Yeah, you see the point. Then you would be a nanometer. So here you're at a fraction of a nanometer, a tenth of a nanometer difference. I'm not going to see that at all, okay? So that's just way too tiny to even conceive. But you can tell the differences here, especially this one to that one. That's pretty big. This one has 50 nanometers. Yeah, you can tell some difference. This one, order of 23 nanometers. Now you're getting down on the order of 14 nanometers or 13. And then, yeah, so you're getting pretty small pretty quickly, okay? And down here, you can't tell any difference at all. So basically, what we have here, let's see, what did they say? Calculate the limit of this Balmer wavelength series where n is equal to, greater than or equal to 3. Well, we did it the hard way by looking at this. And we say it looks like it's going to come up around 364.5 or maybe 0.4. Let's see if we can really, I think I know exactly what it's going to. Anyone want to make a guess? 364.5, okay. Because what? What would be our technique? 364.5 n squared over n squared over n squared over n squared minus 4 over n squared. Divide numerator and denominator by n squared, right? These go out. That becomes 1. This becomes 1. This becomes 0. And you get 364.5. That's what it converges to. So yeah, when you got it 364.50 something, you were getting close. Keep on going, and it just keeps getting closer and closer to 364.5. You'll never actually get there, but you'll get there closer than your calculator can calculate anyway. And that's what they got to. Now, they did it by converting it to a f of x, which is fine, it works, and do the same thing. Divide numerator and denominator by x squared, and you got it. Okay. All right. Now, just a couple more slides here. Here is doing that very thing graphically, taking those values we just had. When n is equal to 3, you're up here in the 600, and what was it? 656.1. I guess that's about right. That would be 760. Okay, it looks like a little low, but that would what? That would be 4 would be down here in the 400s and something. Yeah, 486. And B5 would be 4 something another. And keep on going. You get into the 3s, and after a while you're into the getting closer and closer to 364.5. Okay? Now, what we'll do now is, this is actually the Balmer series when you plot it on the visible light spectrum. Okay? B3, which was your 656.1, this is your 600 nanometers, 700 nanometers. So it's right in here. It's sort of an orangey kind of color. They call it red. It's an orangey red, but it's reddish. The next one down here in the green-blue part of the visible spectrum. Remember Roy, G, the oranges in here. The indigos, they made up violet. Okay. And then B5 is down here, just short of violet. B6 and on. They're in the violet, and they get so close together you can't distinguish them anymore. So they're going toward 364.5. Now, where does violet end and ultraviolet begin? I'm not sure, okay? But it looks like you might actually be in ultraviolet then. Okay? But that's your wavelength in nanometers. So you can pick out, when you look at hydrogen, you'll pick out the reddish, orangish one, the greenish one, bluish, violet one, and everything else you see is violet. But they get so close together you can't pick out. Usually you can get only 3 or 4 distinct spectral lines, and the rest of them are so close together you can't pick them out. Okay. Now we start something brand new, but it's pretty important brand new. Okay? And that's this. It is the geometric sequence. And here's what a geometric sequence is. A sub n is equal to C times R to the n. Okay? That's going to be a geometric sequence. C is some constant, R is some constant. But then they follow this from there on. Okay. C and R are non-zero constants. We don't want C being 0. If so, that's a pretty meaningless sequence. It's 0 forever. If R were 0, that's 0 forever. Not very, interesting sequences at all. Okay? Now, C generally is positive. I guess it doesn't absolutely have to be, but generally it is. R almost always is positive. In fact, you'll see that on this slide. R is greater than 1. Well, why couldn't R be 1? If R was 1, then what is your sequence? C. Constant C always. That's not a very interesting one. If R is 0, it's 0. If R is 1, it's C. Those are not very interesting. So R needs to be something between 0 and 1 or greater than 1. Generally, we go greater than 1, at least for now. Okay? That's called the geometric sequence. If R is greater than 1, the geometric sequence obviously diverges. Now, they left off the C here. They just put it in here. It's starting at C and going from there. Okay? And obviously that's divergent. It's getting bigger and bigger and bigger. Okay. So that's not really all that interesting if R is greater than 1. However, if R is between 0 and 1, then this thing is guaranteed to converge. Okay? We haven't gotten there yet, but just giving you that heads up on that. I think that'll be safe to say. So this is a geometric sequence. Now here is really the good telltale thing about geometric sequence. Okay? Give me a number, any positive number. 2. Okay? You tell me what A sub 2 would be. Okay? I'll tell you what it is. C times R squared, right? You just plug in a 2 for n. What's the next one? A sub 3, what would that be? C times R cubed, right? Now, what is the ratio of A3 to A2? That would be CR cubed divided by CR squared. The C's go out, they've been dating. No, I'm sorry, okay. And what happens here? These two cancel two of those out, leaving you just R. That's what makes a geometric sequence a geometric sequence. The ratio of any two terms in the sequence is always the same value, R. Always. Okay? Now, this one is diverging, but still it is a sequence of numbers, and the ratio of this value here to that value there is R. Whatever R is, to this one is R. Always the ratio of the two values is that same constant R. That's what makes a geometric sequence. Now, and that number R, the reason they name it R is called the common ratio. Ratio, R. Okay. So they give us one. R is equal to 3 and C is equal to 2. So A sub 1 would be, what did I say C was? 2? Just read it. Yeah, C is 2 and R is 3. So that would be 6, right? A sub 2 would be 2 times 3 squared, which would be 18, right? A sub 3 would be 2 times 3 cubed, which would be 54, right? Okay. Right? A sub 4 is equal to 2 times 3 to the 4th, which would be 162, right? I'm not going any higher. I don't keep up with it much past that. Notice what the ratio of each term is. 3, 3, 3. The ratio of every two terms is that constant ratio R, common ratio R. Okay. If you left it just in this form, I will go higher. 2 times 3 to the 5th, 2 times 3 to the... I can write those all day long. And what happens if you do the ratio of 2 times 3 to the 6th to 2 times 3 to the 5th? The 2's go out, 3 to the 5 will go into 3 to the 6 3 times. Every time, okay? That's what a geometric ratio is. Okay. All right, in the next example, we determine when a geometric series converges. Recall that a sub n diverges to infinity if the terms a sub n increase beyond all bounds. So that would be diverging to infinity. So we express that this way. The limit as n approaches infinity of a to the n, if this thing is going to infinity, then that diverges without limit. Okay. And if it was going to negative infinity, it'd just be the same way. So let's do example 7. I think that's this one. All right. Geometric sequence with R greater than or equal to 0. Prove that for R greater than or equal to 0 and C greater than 0, we almost always do that. Now, I don't like the fact they say R can equal to 0. That's bizarre, okay? But they'll take care of that in a minute. Okay. So here's our setup. We wanted to see that the limit as n approaches infinity of CR to the n. Okay? R is greater than or equal to 0. C is greater than 0. Okay? here's what they claim it is, and we need to prove this. They say that's equal to 0 if 0 is less than or equal to r is less than 1. Okay. Remember, c is greater than 0. R is greater than or equal to 0. Okay? But let's just take a part of that first. If it's, let's rewrite this. 0 is less than or equal to r. Okay? Then let's stop when r is at 1. Let's do r less than 1. So that's what that is going to be. Okay? Now, basically what that's telling you, let's take the first part, is really easy. When r is equal to 0, that's obviously 0. Done. Okay? No way around it. Okay. Now, how about r anything between 0 and 1? Not 0 or not 1, but in between 0 and 1. Okay? And you're letting n go to infinity. Well, your c is greater than 0, so everything's positive. That's okay. But you've got an r that is basically a fraction. Less than 1, but greater than 0. Okay? And if you raise that fraction, any old fraction, even 0.9, square 0.9, you get 0.81. Square 0.81, and it starts getting smaller. If you let the n get big enough, that's ultimately going to 0. Okay? So sure enough, for any r between 0 and 1, this will also go to 0. You may have to get in way, way up there before it gets close to 0, but that's where it's headed. Okay? So there's that. Okay? Now, we're doing r greater than 0. So we started at greater than or equal to 0. We started at 0, that's obviously 0. Then anything between 0 and 1 is still 0. What if r, though, is equal to 1? Well, if r is equal to 1, this is merely c, right? If r is equal to 1, raise 1 to any power you want to, it's still 1, and this would just be c, okay? That's pretty simple. Fairly uninteresting, but simple, okay? But what if r is anything greater than 1? It's going to infinity, because now you're getting a number, even 1.1. Square that, you get 1.21. Square that again, you get 1. And it just keeps getting bigger. So when n gets big enough, that whole thing's going to infinity. All right, so that's, I sort of did a quick and dirty of it. They actually take it through sort of one step at a time. I say they do, but yeah, we've basically done it. So let's just leave it alone and keep going. Okay. That last example, this last example will prove extremely useful when we consider geometric series in 10.2, not sequences, but series. The limit laws that we have used for functions also apply to sequences and are proved in a similar fashion, so all they're going to do is give them to you. So that's good enough for me. Okay? And we'll use these after a while as if without even thinking about them, because they do have to be true. They were good for functions. Sequences follow functions. Okay? Here's what they are. Let's assume that we have one sequence A sub n and another sequence B sub n. And both of these are convergent sequences. Okay? A sub n converges to L, which usually does. B sub n, let's just say it converges to M. It's different from the M that you use in the thing, but just for another one. Okay. Then, since both of these converge, the limit of the sum or the difference of those two as n goes to infinity, same as before, is equal to the limit of A sub n as n goes to infinity plus or minus the limit of B sub n. So basically what's it saying, the limit of a sum or difference is the same as the sum of the difference of their limits. Okay? Just like we did for functions, that happens here too. And since this has a limit L, that's a limit M, this is equal L plus or minus M. Okay? So that covers addition or subtraction. This one, the limit of a product is the product of the limits. Just like it was for functions, it's true for sequences as well. And this is L, that's M, so the limit is Lm. The limit exists, it's that number Lm. Now, what if we have the quotient? A sub n divided by B sub n. Well, that's the limit as, the limit of a quotient is the quotient of the limits. So that's the limit as n goes to infinity. A sub n divided by the limit as n goes to infinity of B sub n. And that would be L over M, because that is the limit here. That's the limit there. As long as M is not equal to 0. If that limit here was 0, then you can't do that. Okay? But if it's not 0, that works. It is conceivable. That could be a negative number. That could be. So all the signs still follow. Now here's another one that's pretty important, especially if you get to linear situations, which some of you are in. The limit as n goes to infinity of c, some constant times a sub n, the limit of a scalar product of a sequence is the scalar product times the limit of that sequence. And that would be c times L. For any constant c, positive, negative, fraction, decimal, whatever it is. Okay? Any real number c. Yeah, it's true for 0. It's true for 1. Those are pretty obvious. But it's true for any. Okay. So those are your limit laws for sequences. That's theorem 2. Let's move on to the limit law, to theorem 3, which is the squeeze theorem for sequences. I don't know if you remember this from is that integral calculus, differential calculus, or both? I think like it's probably true for both. The squeeze theorem for sequences. Let's now have 3 sequences, A sub n, B sub n, and C sub n. Okay, that's the what do they call it? Normal term, whatever they call it. They're all sequences such that for some number m, now this m is back to being the thing that we were dealing with before, that for some number m, if you get your n greater than that m, your b sub n is always going to be less than or equal to your a sub n, but that's always going to be less than or equal to your c sub n. Okay? Well, they want to change the order, let's say no. Okay? So that's true for all n greater than some value m out there. That your b sub n less than or equal to a sub n, that's like less than or equal to the nth term for the c sequence to c sub n. Now, let's also imagine that the limit of b sub n as n goes to infinity is going to be L, and the limit as c sub n as n goes to infinity is going to be L. Well, guess what? If this is always less than or equal to that, less than that for some m value, n greater than the m value, and these two have limits of L, then that means that A has to too. Because if B is less than A, C is greater than A, and these both go to L, A's got to go to L too. That's the squeeze theorem. No matter what they're doing before you get there, past M, once you get past M, that's always going to be true that B is less than A is less than C, and if B and C are both going to one limit, A's got to go there. It can't get out. It's stuck between them, sandwiched between the two. All right. I think this is example 8. Let's see if it is. show that, no it isn't. It's not example 8, but we'll do example 8 on here. Show that if limit as n approaches infinity, got some sequence here, up and up and up and up, absolute value of a sub n is equal to 0. So its limit is 0. Then, if that's the given, then the limit as n approaches infinity of a sub n is equal to 0. Okay? Now, nothing to do with that. Okay. Now what this is telling you, that the limit as n approaches infinity of the absolute value of a sub n is 0. Okay? Which means somewhere out there, a could be going plus or minus, but the limit as you go out there is going to be to 0. Because the limit of a sub n, absolute value of a sub n, if a sub n went negative, it's going to absolute value will be positive. And if that is converging to 0, then a sub n itself has to be converging. Because for everyone that's above, this is above. For everyone that's below, this is below. But if the n is greater than the previous one, it's closer to 0, so that a sub n also has to be approaching 0. Okay, that's sort of the arm waving version of it. Let's see what we do here. Okay, what this means, the limit as n approaches infinity of absolute value of a sub n, we know that this is true. Minus the absolute value of a sub n and absolute value of a sub n. This one's guaranteed to be negative, that was guaranteed to be positive. Somewhere in between that is a sub n. Okay? Because if a sub n is positive, then this is going to be equal to that, and this will be less than that. If a sub n is negative to begin with, then absolute value of a sub n will be positive, but then you negate that, that will be the same as that. So you know that a sub n is always in between the minus absolute value and the positive absolute value. Gotta be. Okay? Now, absolute value of something is negative. Negative. But you can negate the absolute value of something, and then it's got to be negative. Right? Absolute value of negative 2/3 is 2/3. The opposite of the absolute value of negative 2/3 is negative 2/3, because absolute value of negative 2/3 is 2/3. When you negate that, it becomes negative 2/3. So if you started out with negative 2/3, then this thing is going to be equal to that, and that thing will be greater than that. Okay? But if you started out with 2/3, absolute value of 2/3 is equal to that, this is going to be less than that, obviously, because that's positive and this is negative. So this is the thing that could be either positive or negative. If this is positive, it's the same as that, and this is always less than that. If this is negative, it's the same as this, and that's always greater than that. So yeah, it fits in between the two exactly. Okay? Now, seems like what we've got to show, they already gave us that the limit of this is 0, right? The limit of absolute value of that. Well, then the limit of this thing is going to be negative 0, right? Well, then this will be, and negative 0 is 0. And this is always in between those two, so this has to be a limit of 0 as well. We just showed it. Squeeze theorem, right? That's the quick and dirty. I think you'll see that's pretty much what they did. All right. Now, example 9. This is the graph. I think of it. No. Maybe not. Okay. Let's do example 9. All right, to erase. Okay. Prove that for C not equal to 0, okay, the limit as n approaches infinity of CR to the n is one of these. Okay? When is that guaranteed to be 0? Remember, C is not equal to 0. It's guaranteed to be 0 when R is equal to 0, obviously. But remember, we also showed that the limit of that as n goes to infinity is going to be 0 when R is less than 1, between 0 and 1, right? So that's between if minus 1 is less than R is less than 0. Okay. Now, where did they get the minus 1 from? It's pretty obvious if R is equal to 0, that thing's going to be 0. But where did they get the minus 1? Oh, I'm sorry. Okay, this is a different problem. It's a geometric sequence is R less than 0. Okay, so your R is less than 0. I didn't read the top very well. So obviously R can't be 0. That's why they left it out. Okay, but if R I've left something off there, haven't I? Oh, no, it's a minus 1. I was reading that as a 2, I thought. Absolute value? No, I couldn't read my writing. If negative 1 is between R is between negative 1 and 0. Okay. Now, remember what happens if you raise a negative number to a power. Now, these powers are always integral values. Okay? 1, 2, 3, 4, 5, 6, 7. May not start at 1, but they're all integral values, right? Now, the R, though, can be any value. We're taking it between minus 1 and 0. Okay. Can't be minus 1. If R was minus 1, this value is, if n is even, that would be a 1. If it's odd, it would be a minus 1. So you have plus C minus C plus C minus C. It would just jump back and forth there. So we're not doing equal to minus 1. We're doing between minus 1 and 0. So it's a fractional form between there. So if n is even, this is positive. If n is odd, this is negative. Because you raise a negative number to an odd power, it stays negative. Raise a negative number to an even power, it goes positive. Okay. So you're jumping back and forth, but R is a small absolute value less than 1, so it stays between that. So it's got to be coming down to 0. It goes above and below, but it gets closer and closer the more you go. So sure enough, that's going to 0. Now that's not done with that sort of visualizing it. What we do is basically what I just said with the evens and odds. If n is odd, that sequence is always, well, let's see. Let's see how they do that. Yeah, basically it's what I just said. It's going back and forth. But if R is less than or equal to -1, it diverges. And why is that true? Because if R is, let's take -2, and raise it to different powers. So the first power would be -2, the second power would be 4, the third power would be -8, fifth power, if it's on, fourth power would be 16, fifth power -32. It getting wider and wider, diverging. Every other power goes positive, negative, but gets bigger and bigger and bigger. Same thing's happening here, except they're getting smaller, smaller, smaller. Positive, negative, always getting smaller. So this type converges to 0, this one diverges. If that's -1, it doesn't diverge to positive or negative infinity, it just bounces between +or -1, which also diverges. Okay. All right. This figure we see here is one that's at the bottom of page 517. However, it's not a numbered exercise. It's just sort of a voila type thing. So I don't think we're going to be able to get it done. So we'll pick up with that next time. Very bottom of the page on this. I had something hold. Oh, here it is. Holding my place here. That will do it. Okay. Homework exercises. This is a longer section than I remembered. Homework exercises. Do number 1. I think I've already assigned that. Do any of the odds 3 through 11. I think I may have assigned those. I don't think I assigned the next group. Any of the odds 15 through 25. Then do any of the odds 27, or either 27 or 29 or both. Then 31 and or 33. Any of the odds 35 through, 61. Either 63 or 65. We did one like that in class. And then either 67 or 69. We did some like that. Let's hold off on that and we'll pick up the rest of those next time. Okay. Okay, that pages, is that what you asked? 521, 522, 521 and 522. And the reason I say odd exercises, the answers to odds are in the back. If you can't get those, bring them to class and we'll work them together as a group. Okay? Good deal. By the way, the test, when we finish whatever chapter we're going to do on the test, I'll try to get questions from the test bank that are as similar as I can to the homework exercises. But if you think the slideshows are bad in this, the test bank is pretty bad too. So sometimes I can't find very many that are very close to these. I'll try to get the ones that are closest. Okay. Good deal. We will